and start recording. So we should all be okay. Let me see. Is anyone on Twitch at the moment? If not, or actually any sort of acknowledgement. Would be great. That would be great. Okay, all right. So you should see some rotating, spinning cubes, triangles, and whatnot, right? And hearing stuff. Good, good. That's good to hear. All right, let's get some video over here on Discord as well. And let's see. Let me even do that for a moment. Okay. So for today, we may be sort of on the shorter side lecture-wise, so maybe we'll be able to get into the check-ins kind of a little bit quicker. Gonna sort of summarize the stuff about chapter 4 using the stacks of transformations. Talk a little bit about that, and also talk a little bit more about the next project and kind of begin to set up some more concrete things in terms of expectations. And I want to also introduce one of the first big requirements that's going to be sort of above and beyond what's covered in the book. So it's a good thing you're all here today, and good thing you're watching afterwards, because I'm going to ask for this as part of the next project. And it's not, I don't think it's covered in the text. I'm pretty sure it's not. So we'll figure that out. So it's going to be great. It's going to be great and very useful and make life a lot more interesting and useful. Not that life isn't already useful. Useful? Oh, okay. Sorry, it's been a long week, hasn't it? How's everybody holding up? Everybody's doing reasonably well, I hope. Let me pop out my video view here and get over to the general view over there as well. Okay, we've got some thumbs up. That might have just been from acknowledging that the stream was working. So let's talk about, let's see, we left off last time right about here where we had the example of the cube and the pyramid, and we sort of went off the normal path, introducing the idea of using multiple vertex array objects instead of doing everything with a single vertex array object, which is what you see in a lot of tutorials. People tend to set up one vertex array object and then just keep changing the buffers around and kind of modifying the state. When really it's sort of supposed to be the basic thing that you set up a vertex array object that has everything to do with all the vertices that you're going to be rendering. And that's sort of supposed to be the hierarchy, vertex array object, and then it's got everything necessary to describe that set of vertices and what they have. So you can do it one way, six a dozen one way, six one way, half a dozen another sort of thing. But now you've got that covered. So if you're going through tutorials, if you're finding other stuff on the interwebs, you can kind of see what that is when you can use multiple VAOs, or you can use one VAO and just kind of keep swapping the state of the vertex buffers and so on. You should feel pretty comfortable with those, because as we go forward, you're going to be doing more and more specifically with the vertex buffer objects as we get into loading complex objects and manipulating them and so on. Make sure, I've been talking to some people, make sure you are not relying on old school traditional OpenGL, where you see, if you see a GL begin and a GL end, that is old immediate mode, ancient, not to be really done that way anymore, OpenGL. Now we live in the land of VAOs and VBOs and retain mode, and where we are setting up the state on the GPU side and doing far less on the CPU side in that regard. So that's why we want to be relying on that and not on the immediate mode. GL begin, lots of primitives, GL end, that's far more resource intensive on the CPU side, which is not what we want. We want to be executing as much as possible on the GPU side, right? That's what's known as modern OpenGL, right? So when you hear people talk about modern OpenGL, that means we're relying on VAO, VBO, shaders, etc., and no more immediate mode, OpenGL. With one bit of exception, which we'll talk a little bit about in terms of GUIs. So there's a very popular GUI called Am Gui, and I'm going to demonstrate that a little bit, and we're going to use that in some of our projects going forward. It's a very popular kind of GUI set that integrates very nicely with not only OpenGL, but lots of different flavors of OpenGL, and also things like Vulkan and Metal and so on and so on and so on. So Am Gui is a really cool, I hesitate to call it library. It's basically usually it's just a set of C++ files and headers, and you kind of incorporate that into your project, and it gives you all sorts of really cool integrated UI elements, things like buttons and text and sliders and input fields and so on. So as we're creating our projects and programs, we can actually put some user interface into it. So you can have a slider to see, let me move that in and out of the scene. Let me change its color interactively. Let me do those sort of things. And those are going to help a lot when it comes to projects and, as you're experimenting. So you're not constantly like changing, implementing, re-implementing, recompiling, and so on and so on. You can really be doing things interactively because, after all, this is real-time computer graphics that we're doing here. All right. So we'll talk a little bit more about Am Gui towards the end, but let's kind of go through a little bit more. Chapter 4. We're going to kind of hopefully churn through Chapter 4 with some additions. So we have the cube and the pyramid. But now let's talk about a hierarchical scene, right? Obviously, our games and any sort of 3D graphics that we're doing, normally there's the idea of a scene. You have multiple objects. You might have characters. You might have backgrounds. You might have terrains. You might have buildings, vehicles, and so on and so on. Lots of things that are contributing to a scene. Rarely is it that you have like one particular object and everything relies on that. Sometimes, but more often than not, you have these hierarchical scenes. So as you have objects in the scenes, it's often useful to implement some sort of hierarchy so that you can kind of understand the relationship of those objects to one another, and then also the relationship of, say, the camera to all of those objects and so on, right? So for this, we often use a matrix stack. So if you've looked ahead in the book, you may have seen this example here, and we'll kind of, this example will be around with us a little bit for the next 2 or 3 chapters now. But let's think in terms of conceptually. Okay, imagine the scene is the universe or the solar system, or we'll focus more on the solar system with this one. And in the solar system, we have the sun, and the sun rotates. And then we have the Earth, and the Earth, or I should say the sun rotates, the Earth revolves around the sun, right? Without regard for the sun's rotation, necessarily, right? The sun doesn't rotate once per year, but the Earth does rotate around the sun once per year. Revolves around the sun, I should say. Then the Earth itself rotates once per day, right? And then there's the moon, which revolves around the Earth, and the moon also has a rotation. So there's lots of different kind of rotations and transformations and movement going on, and they are all related, but they're not all necessarily completely locked together, right? We have the rotation of each of these bodies, which is separate from the revolution around them. But in some cases, even the revolution is dependent. Like, for example, the moon revolving around the Earth, also that moon up there, even though it's going around the Earth, it's also moving around the sun according to the revolution of the Earth around the sun, right? So there is a hierarchy. Some of those things build on one another, others are independent, like the actual rotation of each of those objects might be independent. Or maybe, in some sorts of scenes, maybe they are not independent of one another. But for now, in our case, we're talking about the solar system and the Earth and the moon. We can say, yeah, this is how we're going to identify these things. The moon is revolving around the Earth, while the moon revolves around the Earth, while the Earth revolves around the sun, and all 3 of them will have their own rotation. Okay. So to do this, we're going to work with stacks. Now, so let's talk about stacks for a moment. Hopefully you remember data structures. does everyone my typing remembers stacks from ES? Hopefully, right? One of the most basic data structures. Not going to go into real depth on it. And one of the cool things is we're not going to worry about the implementation of stacks, but we are going to use them quite a bit. So it's important to make sure we're all on the same page with regards to stacks. Okay. Well, here we're not stack versus heap. A lot of that has to do with memory allocation. Now we're just talking about conceptually about a stack here. Our stacks could be local on a local stack or part of a global heap or things like that. But let's stick to a more conceptual definition of stack. Okay, the idea behind a stack is that we have some sort of data structure that we push things into and we pop things out of, right? So the stack will just keep track of something for us, and we'll just kind of keep pushing things into the top, sort of like a Pez dispenser. Has anyone ever seen a Pez dispenser these days? I don't know. It was sort of a candy dispenser that you'd put superhero's head would come back and candy would pop out. And it'd always be the last thing you put in would also be the first thing that would come out. Right? That's the idea behind a stack. Often you hear them referred to as either LIFO, last in, first out, or first in, last out. Basically, that means the same thing, right? If you push something into a stack, you push another thing into the stack, you push another thing into the stack. If you pop something from the stack, it's the last thing you pushed in because you are building a stack, right? It's the idea. Imagine taking a bunch of plates that you're, I don't know if you're at home or your apartment, you take your plates out of the dishwasher and you stack them in your cupboard. And then when it comes time to use your plates, you grab the plate that's on the top. That's the last plate that you put in, which is at the top of the stack. All right, if you get another plate, you push it in there, it's on the top of the stack. You pull out that plate, it was from the top of the stack. So the stack at some point is empty until you kind of fill it up with things, but then you're always grabbing that thing off the top of the stack. Now to do that, we have push and pop. They are the main interfaces to our stack. And also, we can also refer to top, which is just the current element, that element that is sitting there at the top of the stack. Okay. It's great for sort of hierarchical things where we're kind of traveling down. Imagine we have a parent and then there's a child and then a grandchild and so on. And we're always, kind of adding things on, pushing and pushing and pushing on the stack, and we're working down there. And then to get to the next level up, we pop something off the stack and we move there. We want to get to the next level, we can pop something off and we move there, right? So we can kind of keep moving up and down these sort of hierarchies by knowing that each time we went down the hierarchy, we pushed something on the stack to remember where we kind of came from, or remember what the state was at that particular time. So stacks turn out to be very good, if not perfect, for maintaining this sort of hierarchy of transformations that we're going to be doing in our more complex scenes. Right? In certain circumstances, when you sort of eventually have not just parents and child, but you also have sort of branches and siblings, then you have to sort of keep track of things, but ultimately it kind of works the same way as well. If you get to a sibling and you're pushing and popping and pushing and popping for each of the siblings, then you can also, because you push and pop for a sibling, you're still at the parent level. And then you push and pop for that, push to work with that next sibling, and then you pop, and then you're still at that parent level. All right, so they're really, really great for kind of going through, for maintaining state of a hierarchy that way, right? Once we go down, we can move across, and then we can move back up, and so on. All right, so everyone good so far on that? Hope so, right? Everyone got A's and B's in data structures, I assume, because I think that's what if you transferred into Comp Sci, you need a B in data structures or something like that. So assume we got that down pat. Even if you don't, make sure you do. All right, so thankfully for us, we're not going to be implementing our own stack. It is thankfully provided by STL and C++, so that's available for us already. It's there, we will use that. You'll see it used in lots of places in OpenGL for various things, but for now, let's talk specifically about transformations and why it's useful for that. All right, so talk a little bit more about, just to drill the point home again. In C++ and STL, we have certain stack functions. Say specifically, when you push something on the stack, it's basically making available a new entry on the top of the stack. That's the thing you push onto the stack, right? And in our case, we're going to be pushing a copy of a matrix to the top of the stack, and then concatenate additional transforms onto that copy. So that's going to be like the current state, right? We're pushing things onto that. So we say, okay, here we are, push that onto the stack. And then we can refer to that top of the stack and work with that, right? So we're going to actually work with the top element of the stack. Right. If we say pop, it's going to remove that thing from the stack. You still have a reference to it, but it's removing it from the stack, and then it's up to you what you do with it after that. But if you've popped it, then it potentially is gone from as far as the stack knows. Top will return a reference to the matrix at the top of the stack without removing it, all right? So a lot of the time we're going to be referring directly to the top of the stack, so we know, there it is. Instead of referring to individual transformations, we'll be referring to the top of the stack and the transformation that's there at the top of the stack. So, for example, hopefully this is readable in our window here. So we might do things like, applying directly to the top matrix in the stack. We might say, okay, stack top times equals rotate, or stack top times equals scale times equals translate. So in that case, we're just manipulating, we are transforming the matrix. We're concatenating additional transformations to that matrix that's at the top of the stack. All right. So basically, this is the way it looks. You declare a stack, and then when a new object is introduced relative to the parent object, you push things onto the stack, and then you apply the transformations that are necessary to work at that level. Right? So if you had a child object, you would push the state, do the transforms for that child object, and anybody else, maybe you're going to wind up going even deeper. But then if you don't go any deeper, if you're at that child and you want to go back up to the parent, you pop off the matrix that you just made, and so on. Okay, when an object or sub-object has finished being drawn, then you pop its model view transformation matrix, thereby removing it from the top of the matrix stack. Right. So let's concrete example of that. In that example that I showed rotating around here we go. Make some room on my screen here. So here's it in action. So what's happening in this scene? Well, we have, at the center, we have this triangle. And the triangle is representing the sun. Or maybe the sun, I don't know, it's just a thing. It has its own rotation, which is causing it to kind of rotate end over end, right? And it is at the beginning, it's the sort of center of the universe. It's at 0, 0. So it's rotating around 0. So we say, okay, well, now I apply this rotation here, but you'll notice that everything else in the scene is not rotating end over end like this one is. So that means when I'm done manipulating this, before going into the children for it, I pop that rotation off before going down the hierarchy, right? Then the next thing in the hierarchy is this child here, this cube. And it is going to have a rotation around the center, which is the original transformation there, right? So it's doing a revolution around the center. So that's its revolution. And then on top of that, it has a potential rotation. And then its rotation, it's kind of a little bit weird because it's revolving and rotating at the same time. If it wasn't rotating, it would just kind of move and always be facing us, perhaps, or the other way around. So it's doing its thing, and then finally we have the moon object, which is then rotating around revolving around and rotating. So you can see it sort of tumbling in space and following its parent around as it moves. All right. So that's what's happening. The sun's rotation is pushed onto the stack, so that's that rotation end over end, and then it's popped after drawing it, meaning nothing else is going to have that rotation built into it. So at this point, not much has really happened other than we have the view matrix on the stack, right? We push the view matrix on the stack. The sun's rotation is then also pushed onto the stack and popped after drawing it. After that, the planet's revolution around the sun is pushed onto the stack, but is not popped. Why? Because we want the moon, we want the children of the planet to also revolve around the sun according to that same revolution. However, the planet may rotate. It's rotating around its center. So we push the planet's rotation onto the stack. But after we draw it, after it's rendered, we pop that rotation back off the stack so that any children are not rotated. All right. So that's why it says planet's rotation is pushed on the stack and popped after drawing it. Then the moon's revolution around the Earth is pushed onto the stack, but not necessarily popped, because at that point, it is going to need to rotate according to that revolution, right? So the final action is that the moon is rotated. That's the last thing on the stack there, the rotation of the moon. And there's nothing at the end because we don't have to worry about going back up in this case. There's no additional rendering. There's no other, like if we had multiple planets in the solar system, we would then actually go pop the moon's rotation off, pop the moon's revolution, pop the Earth's revolution, and get back up to that, and then we can figure out the revolution of the next planet around, okay? So at each drawing step of the example, the matrix on top of the stack is always the one that's serving as the MV matrix. Notice the projection matrix, the perspective matrix, didn't even come into the equation because that one is constant, right? That's going to be the same for the whole world. That one's just going to be applied on top. So at the end of the display, the remaining matrices are popped off the stack. If they're no longer necessary, you just get rid of them. All right. So this is what that looked like. And let's do this. I want to take a look at this actually in situ, so in its own, as it exists in here. So we're going to go to the chapter 4 matrix stack here. And the reason I want to do this is we're going to see what happens if we don't pop certain things off the stack. So we'll see what exactly happens. So let's start off with the matrix stack, and we'll just go ahead and rebuild it to make sure that everything's okay. It probably was because it was still rotating, but we'll make sure. Rebuilt it, everything's seated. I run the local debugger version, and I'll bring it back over, and sure enough, it's doing exactly what it was doing. Notice everything, the Earth is on this plane, right? It's not rotating up and down. So say I wanted the rotation of the sun to affect the revolution of the Earth. Let's set this over to the side here. So I want the rotation of the sun to affect the revolution of the Earth. Here's my program. And normally, if I look in my display function, what's happening is I start off and our view is being put there, right? So our view is the first thing that gets put on the stack. And then we have the sun at the center. So we push the model translation, in this case, it's not much of one here. And then we push the rotation, and notice it is getting multiplied each time to do that concatenation. And then we go ahead and we basically say, draw arrays is the important part, right? We set up everything, we bind the buffer that belongs to that triangle, so this is the pyramid, I should say. That one is the one that is bound, and the MV matrix here, the MV stack is the one that's getting passed to our uniform matrix, and it goes and on through. And the last thing it does here, like I said, it pops that stack, one thing off of the stack, which is why the Earth doesn't do that rotation. So let's go ahead and get rid of that pop. So now, with that pop out of the play, let's see what happens. So now, as the sun is rotating, the Earth is actually, the Earth's revolution there is affected by that rotation. So you see it's kind of going up and down in what looks like sort of a figure 8 pattern based on the relationship between the two. Right. Far more complex. Let's make it even more complex. Let's say, all right, after the Earth, the planet, let's not have this in sync with that, or let's make it in sync with that, I should say. So we will remove this pop and go ahead and build that. So we're making our orbits and everything more and more dependent on one another. So the degree that they're changing, it's kind of it's a pretty complex relationship, but all I'm doing is, you know, changing what gets pushed and popped according to here. Right. So let's put those back. Let's go ahead and put those back. And maybe instead, I'm trying to think, if I would have to, if I were to do this, if I were to say, okay, I pop this, and then I were to pop the other matrix for the cube for the planet, let's see what's going to happen. So now the child, the moon, is not going to be affected by the planet's rotation, if I'm predicting that correctly, right? Because we have popped both the rotation and the translation off the stack. So let's see what that looks like. I have a runtime error. Abort. Interesting. DQ empty before pop. I must have left an extra one around. All right. So we did a push here. We did a pop. We did... Is it that... Oh, yeah. All right. I think we went one step too far here. Right, because we put the pop here, we have to remember to not do the pop at the end there. Important thing about stacks. You have to remember that you can't pop things off an empty stack. All right. So what happened? In this case now, what we've done is we have basically said, okay, the moon, because it is not following the revolution of the planet here, we moved it up, and now its revolution is around the sun instead, because we popped our way back up the stack sort of early. Right? So, pretty straightforward application. Right? It's always a matter of you're always just keeping track, and you're usually, you know, it's going to depend. If you have translation, transformation, a translation, a rotation, a scale, you know, it's depending on how your motion is using, but typically it's going to be a translation and a rotation. As you get into animations, you're going to have, you know, you very often are going to be doing things like animating a skeleton according to a hierarchy like that, right? So every bone in a skeleton, that's going to define how an object moves. Every bone potentially has its own translation and rotation. All right, so if you have the thumb of the skeleton somewhere, by the time it gets to the thumb, then the whole model has been rotated. Then the shoulders is the rotated, translated. Same thing for the shoulder relative to the body. Then maybe the arm had moved, so that might have a rotation. So this upper arm, lower arm, hand, and eventually thumb, and each of the bones in the thumb potentially. So if you have bones in a skeleton, you're going to be using the heap. Excuse me, not the heap. Anthony's question got me confused now. That stack in order to implement that sort of motion. Okay. Everybody pretty good on that? All right. So it's a matter of try. So things are, hopefully you're finding that, we're sort of following along in the book. There's lots of good examples, in the book. It's pretty straightforward. Again, I specifically chose this particular text because it does work very much like a lab manual, and it introduces the right things. There's lots and lots of information about OpenGL out there, and unfortunately, OpenGL fortunately and unfortunately, OpenGL is mature enough to the point where now there's successors to it, but it's still a really good foundation before you get into more complicated things like Vulkan and Metal. But it's important to kind of be at the point where at least we have to be looking at the things that are sort of acknowledged as sort of the highest or the state of the art, the modern versions of OpenGL. Right? So please do make sure that you're following along in the book and getting to that point. All right. And now we want to sort of veer off some of those things. All right. So one of the things that I have discovered, though, is if you do want, I'm not saying that you shouldn't try other tutorials and look for other information out there, especially as you get into your projects. There's lots and lots of great inspiration. I have been posting in both the project ideas as well as resources, and I'm trying to find resources that are of modern OpenGL. And the more recent one I found was the site learnopengl.com, which has some really good tutorials on it, as well as even they have a basic implementation of a breakout sort of game as a 2D game using OpenGL, which is really cool. The big difference between that particular site and the stuff we're doing in the book, however, and this isn't that much of a departure, so if you want to look at that, bear this in mind, is they're using GLAD rather than using glue. Right, so there's lots of different potential interfaces to OpenGL other than glue. Glue being a popular one. It's going to be used in some of your other courses if you've taken advanced graphics, or you're going to take advanced graphics, or you're going to take computer game engine architecture. We're using glue in those classes. But GLAD is another way. Thankfully, it's pretty straightforward because ultimately it's just a mapping, to OpenGL functions. So if you can be clever and creative, you can easily kind of map your way across without too much difficulty. So the learnopengl.com is a really pretty good resource, and there's some good examples of what people have done with it there. So I'm giving that a thumbs up as far as that. So always be looking for modern OpenGL tutorials and lessons and inspiration. So that's one of the reasons it came up in some of the projects and things. So the moment you see GL begin and GL end and draw vertices, that's when you get nervous. That's not modern. That's not considered modern OpenGL. All right. So let's see if I can find my PowerPoint. Let's get back to the PowerPoint. All right. I thought that was a more fun way than just kind of stepping through the code here, but ultimately you'll see that we pushed the first element on the stack, and then we can refer to that, we pop it off eventually, and so on and so on and so on. All right. So another few topics that we want to mention and talk about is the notion of some more primitives and culling. And these are general concepts, but primitives specifically, we're going to refer to them, in terms of the primitives that are OpenGL. we've been mostly dealing with GL triangles and GL triangle strips, right? This is a good slide, showing you what the difference was. There's a little bit of questions before about, well, how many vertices does it take to actually specify a triangle and, in your buffers. And this is a pretty good diagram here, you'll see. In GL triangles, each triangle is a set of 3 vertices that are individually specified. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. Then you have the opportunity of using a triangle strip, in which case each vertex builds on the previous vertex, right? So the first one is 0, 1, 2, then the next one is 1, 2, 3, the next one is 2, 3, 4, and so on, right? And there's a few more that we didn't really talk about last time, the notion of a GL triangle fan, which is kind of an interesting one in that pairs of vertices, each pair of vertices pass through the pipeline, form a triangle with the very first vertex. So you can have things that are, in the case of a fan, you have a common center point, right? 0. And then you might have a triangle that's 1, 2, and 0 that's 2, 3, 0 that's 3, 4, and so on, right? So we're getting some economy of scale in that. Notice that 2 is repeated in the second triangle, and 3 is repeated in the third triangle, and so on, right? Similarly, we have some structures for lines the same way, where we can have a line just between 2 points, or we can have lines that are formed by strips that work there. All right. Now, the reason I'm bringing that up now is also because not in chapter 5, but in chapter 6, you're going to be looking at, both cases. Chapter 5 and chapter 6 is going to be handy to keep this in the back of your head, because in the case of, as we're getting into texturing polygons or texturing triangles, you're going to want to be thinking more in terms of a model level, where a set of a texture or an image texture is going to apply across a whole model as opposed to an individual triangle. Right, so some reasons to keep that in mind. And then in chapter 6, we're going to be looking at specifically loading models that were generated by other programs. So the first one, we're going to be looking at OBJ files. And I think there were some things that were created by Blender that we can use. And the other reason I wanted to mention the learnopengl.com a second ago is that those particular tutorials also introduce another technology that winds up being used, or we're going to be using in game architecture and so on. It's a library called ASSIMP, right? It's a SIMP. It is a object loader or a model loading library. It's a little bit more advanced. It is a library for loading all sorts of different formatted models. In chapter 6, we're going to be doing it by hand. So the text has an implementation of an actual OBJ loader. But if you want to go beyond that, you want to get more elaborate and look at like what we're going to eventually be doing in game engine architecture, you can look forward to a SIMP library to see how that works, right? And there's an example of that, I believe, in the opengl.com. Let me pull that site down here. I really like this one a lot. Oh, the other cool thing about this site is it has a text. It is available as a PDF file. They'll even go ahead and give that to you as the PDF file. Lots of good examples in there. The typical, once again, all the favorites that you're pretty used to by now. And then some of the more advanced stuff that we're going to be talking about. And where is that? Model loading. Yeah, they are using a SIMP library, and they will even then do some abstraction when it comes to, once you load a file, they have a particular implementation of meshes and models. So we may try to, I may try to kind of align what we're doing in the text along with this notion of just one example of meshes and models in there. If they don't align properly, it might pull a bit from here. So that's going to be useful, especially as you're getting into sort of creating, a lot of people are interested in game engine sort of things or graphic engines. So having meshes and models in there is quite useful. Something to be having in mind. So great resource over there. So keep that in mind as we get especially into chapter 6. All right. So let's keep the primitives behind us now. And also this idea, I've mentioned it a little bit in passing before. When we were talking about triangles specifically, we mentioned the winding order of a triangle. The winding order was basically, if you look at the way that the vertices are, as you traverse the vertices according to their view by the OpenGL camera or renderer, are you going through them in clockwise order or counterclockwise order? Right? Are you getting, according to the render 0, 1, 2, or is it wind up being 0, 1, 2, clockwise or counterclockwise? That's what's determining whether or not the triangle is facing the camera, or facing towards the camera, or facing away from the camera, the renderer, right? So when we're creating objects that specifically aren't just sort of a billboard, now in some cases you might want to have both sides visible. So imagine you had a billboard, you had a piece of paper, something that is just a flat surface or a flat mesh, and if it rotated, you might very well want to see the back of it, right? So you want to spend the time to potentially render that if it's facing the camera, right? But if it's not facing the camera, if it's inside another object, then you're going to wind up having, if you have this sort of notion of objects that have their normal, or faces that wind up having their normal facing towards the center of an object or facing away from the camera, those are also known as closed objects, right? They have a skin around them, or skinned objects, right? A sphere, you can't see a sphere from the inside, so therefore you probably want to cull the faces that would be on the inside. You want to say, okay, they would never be visible, right? And backface culling is usually just this concept of not drawing any faces that are facing away from the camera, right? So even if you have the case of the single piece of paper, the side of the paper that's not facing the camera gets culled, or it does not get drawn. We don't pass that. We don't go through the whole process of trying to shade that. Put the fragments for it, right? So we use this winding order and the normal to figure out, okay, which side of the triangle is facing the camera, or facing away from the camera, and we use backface culling to save time by not render faces that are hidden, right? And we can figure out, are they front or are they back according to their winding order. Normally clockwise or counterclockwise is specified to the renderer, so the renderer knows which is which. And you enable it, so there's a function called GL enable for GL cull face. And then you can specify it which are the front faces in clockwise order, or are they in counterclockwise order, right? You can also tell it, should you cull the front face or the back face, right? So you have some choices. When would you use one versus the other? There is a homework question that's on that one. If you do choose to provide an answer for that one, so you should think about that. When would you use the various culling modes, and would you ever cull both faces? You can actually set it to do that. So when would you use those things? Leave that for you to sort of ponder and jot down some notes on in case that comes up. So that's the basic idea behind culling. You'll hear that term come up. It's basically we want to save time, we want to be efficient, and not render triangles that are not facing towards the camera, right? They become sort of invisible. And you do see occasionally some weird artifacts and so on, especially as models kind of hit the clipping planes, especially the near clipping plane. You have to be careful, okay, is the clipping plane inside of an object potentially? And then, well, okay, you should cull all those faces because they are, not, the faces that you're seeing are the ones inside the object, and you wouldn't want that to see. But if you went into a room, obviously you wouldn't want them to be culled. So that's going to change depending on what your goals are. So that takes us to the end of the chapter 4 materials officially. All right. So let's talk about project 2 just a little bit. and what my expectations are, and then I'll talk just a little bit more about Am Gui and Dear Am Gui. I'm not going to go into a lot of detail on how to implement it because there are lots of resources out there, and it's pretty straightforward. I want to leave that for a little bit later. So, Project 2. Basically building on chapters 1 through 6. I know it said probably 4, 5, and 6, but of course, to get to chapters 4, 5, and 6, you would have had to understand what's going on in chapters 1, 2, and 3. So we'll just say it has to do with chapters 1 through 6, builds on everything so far. Okay. As usual, as with all projects in this class, expect to be using proper, demonstrating proper use of VAO, VBO, and shaders. Basically, proper modern OpenGL. Right? So these concepts will carry forward. Want to have demonstrated some sort of scene with some sort of hierarchy of motion or transformation, probably, possibly animation, or use your imagination. How do you want to do that? Okay. Yeah, if you had, I guess it depends. You could do some interesting things with regards to models that were related to one another and so on. A object gets into a car, or a car travels around the track, and you have, anyway, things like that. So you have to have some sort of scene hierarchy. You should be demonstrating basic texturing, and this is going to come later. This is mostly in chapter 5. And by basic texturing, I mean diffuse or albedo texturing. Diffuse technically is the right term for now. The type of texturing that you've seen, just basically the color of light that's at that fragment, that's reflected at that fragment in a very, very simple term, diffusely lit, right? So it's basic image texturing. What albedo texturing normally refers to is sort of basic image texturing, but the texture itself has been processed a bit to sort of reduce the amount of shadow present in the texture itself. Right, so that as you get into more complex lighting modes, and as you get into more complex things like bump mapping and height mapping, all those sorts of things, then you don't have shadowing, shading, and so on sort of already built into the texture as much. Now, obviously, some of it is going to be built in because that's the nature of a texture, but albedo texture is generally referring to sort of diffuse maps, diffuse textures that have been having some of the depth and some of the shading kind of baked out of them so that they work better when it comes to more complex forms of shading. But we'll just refer to really as diffuse shading for now. You should use at least one OBJ model, or if you want to go further and you want to use the Assimp library or something like that and have some other library or load a Blender model directly, that's fine. But there should be at least one OBJ model that's used. Right, so you're going to need to use an object loader and do something with it, at least one. All right. I'd like to see you implement interactivity or some sort of test capability by using Am Gui. Right. So the reason that I really want to introduce Am Gui at this point because, for example, this is a really, really simple toy example that I cooked up. I just wanted to make sure that this wasn't. I'm not asking people to do anything super crazy. And the idea is that I have this extras project, which I'll again just make sure rebuild. And this is my really dumb program that does the one thing that I did warn you not to do, and it's basically, it is using this, drawing a single triangle with that, but it doesn't really need to. So, breaking my own rules. That's the one case where you're doing this. If you're just testing something to make sure it's running, yeah, you can use GLBegin and GLEnd to test something else. Okay, so this is Am Gui here on top of my basic example. So I've got a little demo window and a little button on it, right? And Am Gui will allow you to do all sorts of things. Like I mentioned before, you can have input fields and sliders and buttons and all sorts of cool things. So, for example, and I didn't do that. I literally did this in 20 minutes before class this morning. But the idea would be to have perhaps, a slider, and then as you use the slider, it's going to be rotating the model or changing the color or, changing the relationship between things and so on, so that we don't have to always just be relying on compile the program and do something. Even you can use Am Gui in coordination in conjunction with the GLFW to get key presses and mouse clicks and so on, so we can have a bit of an interface to your programs, right? So just wanted to put that out there. There's lots and lots of good resources for Am Gui. I'll post some of those. It's really pretty straightforward to set up. I'll just give you a little bit of a lowdown on it here. This is my really, really dumb program that I just created basically to make sure that GLFW and Visual Studio were correctly installed on a machine, and I later on added Glue and Am Gui in here, right? So there are 3 H files. If you get Am Gui, you're normally going to get a set of include files. One which is just the general Am Gui file, and then there's going to be one depending on what version of OpenGL we're doing, and you'd be using OpenGL 4 or 3, and this one 3 works with 4 or 3, and you can do it in previous versions as well. And then whether or not, in our case, we're using GLFW as being our kind of Windows interface to that, or sorry, OS level interface to it. So we're using GLFW. So we include those 2 things, or those 3 things, sorry. And then the project itself is just, it's not, you can build a library if you wanted to, but one easy way to do it is you can actually just build imgui.cpp, imgui draw, the implementation, the OpenGL piece, the widgets. You can all just build that directly into your application, right? So if you wanted to, the idea is that, of course, if you wanted to modify it, if you wanted to customize it, if you wanted to leave certain things out, it's really going to be possible to kind of, go in deeper on there. And you can see that there is lots of things, buttons, images, checkboxes, radio buttons, progress bars, what else? Bullets, etc., etc., etc. Lots of different things. Combo boxes, slider boxes, input scalers, etc., etc. Lots of great stuff. So whether you decide to just include the C++ files and the headers just directly, that's totally fine. Or if you want to make your own library based on that, or you want to use sort of a pre-baked version of it, that's totally fine. But the main idea is, of course, that it will afford you some basic ability to be interactively working with your programs, not just compile and run, right? We want to see that everything functions correctly in real time, and perhaps even doing things like advanced, get to the point where maybe you can load models on the fly, or perhaps you can draw textures, or perhaps you can, do texture mapping or scaling or UV mapping or UV unwinding and so on, right? This is, I think, the other piece of the equation to really interactively work on things. All right, so let me double check, go back to general. I haven't seen anyone really type much on here. So it is pretty, I'm trying to keep, as usual, keep things pretty open. I know you guys, girls, folks, everybody has lots of things going on, and it is a, very complex, very stressful semester. Do let me know, again, kind of what's going on in other classes, if there are any issues. If I did this career fair today, some people at that, they talked to me about it, that's totally fine. And I'm up for that, but I do, of course, want to make sure that, you feel that you're getting what you need out of the course, that you are learning stuff, that you are, these are going to be things that are going to be useful. Certainly as also looking at various postings in game companies, and people are looking for engine developers and low-level developers, and, basic OpenGL is always, like a great experience to have, and fluency in that is great to have. So hopefully this enables you to have some good things ready for you. But do continue giving me feedback if you are having issues and stuff. Want it to be deep so it's useful, but I also don't want to overstress everyone because it's a crazy semester. That said, I want to make sure that you are keeping up once we all agree on things like, that's why we do have requirements. So double check with me if you are going off on any tangents above and beyond, or you're not sure, if you want to do something in Vulkan or you want to do something in some other, it's not modern OpenGL, or it's really diverging from kind of where the basics in the book are and so on. All right. On that note, I will stop the streams. We'll post these streams later, and we'll do a quick check-in with the folks, anyone who hasn't had the check-in yet. And so far, oh, wait, we do have a question. Oh, Owen said thank you. All right, that's good. I love that sort of thing. Let's see. I'm trying to find my. Sorry if my screen starts flashing all over the place. Signups. That's what I'm looking for here. All right, there's the signups. Yeah, I find the Am Gui, to me, that was like I didn't get to spend too much time with it this morning, but I find that kind of exciting, the notion of doing it interactively, and it makes it different when you can really see what's happening on the screen in response to things. Cool project would potentially be, imagine you could create a box over here on part of the screen and allow, basically create a little paint program in the corner of the screen that then that texture interactively, as you're working on those textures, are being put on your models. That's a cool thing. Some way to manipulate stuff like that. Does oh, okay. Good question. Very good question, Owen. So does Am Gui draw the stuff using the same OpenGL stuff we are using, or is it somehow different window entirely? Okay. It uses the same context. I got on a little bit of a tangent here. So let me show you. Okay. So these are things that got included in the main here, in the main program here. You'll see it looks very similar, GFLW init and hints and so on, creates the window, GLFW make context current, and then we initialize glue. Make sure you do need to have glue initialized here, so everything's fairly normal up until that point. Then we have the initialization of, and sometimes you refer to it as dear Am Gui, which is, I guess, sort of it's still Am Gui. You'll see some people refer to it one way or the other, but it's become sort of generally referred to as dear Am Gui. The setup right here, it is using the window that you had set up for GLFW, and then its context is going to be just basically inside of the main draw loop. Like as you had, you're going to have some things where you can set it up for starting the next frame, but it's within that same window. So it has some bit of its own context. It is using its own shaders, for example, right? So this is one of those cases where you're potentially using multiple shaders. It's using its own vertex array objects and all that sort of inside there. That's why we're telling it that we're using OpenGL 3 or 4 and so on, so they can work alongside that. And then in here, it will render within that loop. Now, an important thing, one of the reasons it is called Am Gui, and this is sort of like, ooh, suddenly I get a little nervous. Am Gui stands for Immediate Mode Gui. Okay. So, it is different in that the GUI, every frame, we are setting it up. We are doing stuff every frame as it's being rendered, right? It's not relying on retained state. Yeah. It's not relying on retained state and efficiency as much as we are doing with all of our normal modern OpenGL, right? It has been around a while and it will continue to be. Am Gui is going to be, it's used in Vulkan apps and other things as well. But it does sort of straddle that area, that landscape in between. It is immediate mode in that you're drawing it basically every frame, right? So that's what's going on in here, right? We are actually specifying on every frame, okay, here is the beginning of the window that our Am Gui object's going to be in, and then every time we draw that button. And every time, then when it's done, we say end, and it has a renderer and so on. Why is that? Well, because it's a GUI, because we have to know about user clicks and mouse movements and that sort of thing, right? The GPU doesn't know about those. The GPU does not interact with the mouse, with the keyboard, with joysticks, and so on. All right, so that's why it makes sense for a GUI to be in immediate mode like that, okay? Because ultimately, every point and click is something that is being handled by the CPU, not the GPU, right? So that's what the IM is for, immediate mode graphic user interface. So again, there's always something that will break the rules in terms of why we do things a certain way and so on. But it does sit in nicely there, and I will feel the pain as you do as well, and kind of continue implementing here. Hopefully, for next week, I'm planning on implementing some Am Gui stuff on top of the Chapter 5 and Chapter 6 stuff. So you'll stay tuned for that. Okay, we'll get more into those bits. You don't have to worry about those just yet. You're still deal with Chapter 4, work through that, get things to happen, and then if you want to start moving ahead to Chapter 5's when it starts getting really cool and fun with texture maps in there. I think that's like good stuff. Okay, any other questions? Otherwise, now we definitely want to be doing, and I have for today, ZHUANJ2, ZHANGH21, LAFUEJ, SRIRAA, and DEMARJ3. So some of you I can pronounce, some of you. Oh, when's the project due? 2 weeks. I have to go back and double check. I believe that's probably about right, but it is in the syllabus. Okay, so as long we have in this class, we've been doing pretty well in terms of keeping up with kind of the weekly things. But definitely, as we cover chapter 4, 5, and 6, you should have everything you need certainly within there. Oh, so let me make sure. Wow, I get distracted. All right, so you have an OBJ model, you have Am Gui, which we just talked about, and there should be one other feature of your own choosing, right? It's always like go beyond, make it your own, demonstrate, it should be an actual, sort of a portfolio sort of thing that, you can use it as a discussion as part of an interview, or you can demonstrate it or put it on a web page or whatever, so that it shows, some unique initiative there. And maybe it does become the foundation of, some other project. There's no saying that your project can't progress throughout the course of things. So if you are thinking like even longer term that perhaps, you have some grand vision for your project 4, start talking to me about that, direct message me about that, and we can say, all right, how do we get there from here, and how do we make sure we cover the bits of chapters, all these other projects along the way. I believe it is roughly 2 weeks though, so should be pretty reasonable to do. Like a lot of this is covered in the books, so you should be able to get there. All right. Okay, so I am going to stop the streams. Don't cross the streams, and then call out to people as necessary. All right, have a great weekend. For those of you who I haven't checked or I've already checked in with, have a great weekend. Keep up with the examples in the book. Again, remember, approach it as a lab reference. Look at that first, and then you can find other references built on that. But make sure you're doing things the same way we're following along in the book. Okay, take care. Have a great weekend.